We have already discussed a priori algorithm. Now let me get into the algorithm with an example. So step by step we will be discussing what is algorithm, what are the steps of the algorithm, what does it means, and with an example. So first step of a priori algorithm is frequent item set generation. So let's get into it. So this is the algorithm for frequent item set generation, that is a priori of t. Here the first step is C1, initial pass t, F1, the first frequent item set. So this is how the whole algorithm works. Let's get into detail. The first two steps is C1, we will have the initial pass of the whole t, that is the whole transaction t, whole transaction set t, and F1 will have what, all the values which have support greater than or equal to minimum support in F1. After the initial pass, we will have the elements with support greater than or equal to minimum support in F1. So that is it. So here in the example, this is our transaction set, and C1 is this is the C1, first candidate set, that is A, B, C, D, E, F, 3, 2, 2, 1, 1, 1. So now our minimum support is 50%, so at least the value should be 2. Now from the C1, what I have to do? I have to prune it. So what I have done? I have removed those items which are not frequent. So here D, E, F is not frequent. So I have removed, and now I have got the F1, that is the first frequent item set A, B, C. So this is the first two steps does with the data. We first create C1, where we have the initial pass through whole elements in transactions. We will calculate its support, and we will second step is to prune the elements which doesn't have minimum support. I would prune it off, and then I would get the F1, which is A, B, C. Now let's get into the 3 and 4th steps of algorithm. The third step of algorithm, the third line of algorithm, is a for loop. It says K means the iterations or the pass. So it says the first iteration is already over. We have done we have calculated C1 and F1, we have found it. Now the second iteration. In the second, so K equal to 2. That is, we are starting with second iteration. Fk minus 1 is equal to null, means no more frequent sets are there. Now I can't combine anything again and create other frequent item set. No more joining and pruning process is possible with the available frequent item set. That is the condition where we say Fk minus 1 equal to null. Then K plus plus. So this is the for loop which explains this one, this line 3. Line 4 shows we are calling a function, that is candidate generation function, which would create the candidates for CK. Now I am passing a value for the function, that is Fk minus 1. K, here the value of K is 2. So Fk minus 1 means K1. That is the value of K equal to 1. That is, hence pass F1. Which is F1? This one is F1. So I am passing that particular F1 for the candidate generation function. Now with the example for loop, here Fk minus 1 is what? This one. I am passing F1, which is this one. Now the control moves to the candidate generation function. I have called the candidate generation function here in this example, in this line, 4th line. Straight away the control moves to candidate generation algorithm. This is the candidate generation algorithm. So here also we will move step by step. At the first step, the CK is null. We don't have any combinations. We haven't done any joining or pruning process. So at present the value of CK is null value. Now C equal to null, K equal to 2, hence C2 is equal to null. Obviously it is clear, I hope, because in the previous step I said K equal to 2. In line 3, we can see in line 3 we have initiated the value of K equal to 2. So that has been shown here. value of ck equal to null, k equal to 2, hence c2 is equal to null. Now first process is joining step. These are the steps for joining. Line 2 to 7 shows the joining process, and next is pruning. Line 8 to 11 of the algorithm shows the pruning process. So joining steps are this and pruning steps are this, and 12 to 13 shows the end of the joining process and the returning of the value of ck. So this is the whole structure of the algorithm. The candidate generation algorithm first initializes ck to null, then does joining process, then does pruning process, and then ends the joining process and passes the ck value. Now let's get into deep. Let's get into detail. So what is the process? Here for the for all f1 and f2, line 2 says we have the value fk minus 1, that is f1. In f10 using f1 we have generated two frequent item set f1 and f2, and that should be combined. How f1 and f2 is generated is being explained in line 3 to 5. That is, f1 should be this one, f2 should be this one. That is, f1 should be I1 to ik minus 1, f2 should be I1 to I dash k minus 1, and ik minus 1 should be less than I dash k minus 1. Ik minus 1 should be less than ik minus 1. Then in line 6 do joining process. Here we do the joining process. Here we combine that candidate to ck. With an example, we passed f1. We have the f1 a, b, c. So this is the thing which has been passed to the algorithm. Now f1, that is the first, from fk minus 1 we have generated two frequent sets, f1 and f2. So f1 is ab, f2 is abc, where b should not be equal to c. ik minus 1 is b, I dash k minus 1 equal to c. b is not equal to c, b is less than c. These are the two conditions which has to be satisfied. Now how to join the process? f1 is ab, f2 is abc. Always join the element with the highest element. So a will be combined with ab, ac, b will be combined with bc. That's how we got the, after the joining process we got the ck's, that is the value of ck is ab, ac, bc, and ck are denoted by c. That is, the candidates of ck is denoted by c. So here ab is c, ac is c, bc is c of ck. So this is how we did the joining process for the whole algorithm. Now next is pruning process. These are the steps of pruning process. First, for each k minus 1 subset S of C, that is, our candidate are AB, AC, BC. So for each candidate AB, AC and BC, I have to find k minus 1 subset of AB, k minus 1 subset of AC, k minus 1 subset of BC. So AB, it is A and B, AC it is A and C, BC it is B and C. Non-empty subset is not allowed, and it is k minus 1 subset. So I can't have a subset AB itself. So these are the possible subsets. Now what is the next step? Which is fk minus 1? My fk minus 1 is this one, ABC 3, 2, 2. This is my fk minus 1, which I have passed. Now what is the next step? The subset of each candidate, that is AB, AC, BC. In these candidates, the subset of A, B, A, C, B, C are frequent items in what? Fk minus 1. That is, if S, for if it is the case of AB, if S, that is A or B, is not an element of fk minus 1, then delete k. But here in this case, A, B, A, C, B, C, all are the subset of different candidates of the set ck, and everyone A, B, C, all the three are having minimum support value and they are frequent. So all the candidates should be a part of ck, they should not be deleted. So ck remains as it is. So after joining and pruning process, return CK. We return the CK. CK is equal to AB, AC, BC. Now we return CK. Now the control moves back to a priori algorithm for frequent item set generation. We came from the first algorithm. Second algorithm is traversed. Now we move back to first algorithm with the value of CK in hand. So in the in the frequent items set generation algorithm for the line 5, for each transaction T, which is an element of T, we have to go through all the transactions, and again we have to go through all the candidates in CK, and we have to take the count of CK. That has been here explained here. T, check slide number, we have explained it. So I am going through T, I am going through all the transactions in T to find out the count of C, which are the candidates of CK. So that is the process. So C dot C plus plus count plus plus gives me the count of the value of C in T. So here I've got A, B, B, C, A, C. The support is 1, 1, 2. So that's how I have found the support value. Now after finding count, let's go back to the algorithm. What we have to do? Here algorithm, I have found the count. Now this for loop is the end for. This end is for this particular loop. That is, after I go through all the candidates of CK, I will found the count of all the candidates in this, and then I will end this particular for loop. And after that, this is for showing that we have to go through whole transactions. So loop ends when count of all the candidates in CK is calculated. So this process will stop when I have found the count for all the candidates in CK. This shows for all the candidates in CK. This shows for throughout the whole transactions. So this whole process continues until I take the count of all the candidates CK in C. Now what is the next step? FK I will check whether the candidate C dot count by n is greater than or minimum support. So what I have to do? I would add it to FK. Clear? So that's it. I will explain it again. After I have found out the CK value, I have generated the I have got the candidates from CK. What I would do is, I would go on calculating I would take each candidate in CK. I will calculate its count in the whole transaction. I will go through the whole transaction. I will check out how many number of times the candidate C has appeared in transaction T, and after I traverse through the whole T and I have found the count of the candidate for a particular candidate C, I would check whether its support is greater than or equal to minimum support. If yes, it would be added to the FK. This process continues until I go through the whole candidate. I will go through the whole candidates in CK. So that is what is explained here. So here AC is equal to 2. It has a support. So next is CK. In this algorithm, this end for loop is for this one, this for loop. So this shows that end as no more combination is possible with AC, which means FK minus 1 is none. So this process has to continue. This candidate generation function has to continue until we get a combination which could not be further combined. So that is what it gives. So we combine AC to this. Now no more AC could be combined, and that is how we generate the algorithm. So thank you. Hope it is clear.